Hey, it was brought to my attention that there's some audio problems with the screencast, so I'm re-recording it. So this screencast is about the differences between conventional and nuclear power. Okay, so conventional power, which is by burning coal primarily, but also by burning natural gas. And just so you know, the difference between burning coal and natural gas, really the difference is how much particulate matter is produced. Right, that's and a few other things, but that's the main difference. So, but in order to make electricity from using fuels, whether they're chemical fuels like natural gas or coal, or nuclear fuels like uranium, in both cases, the potential energy is being released as heat. And in order to convert heat into electricity, you've got to boil water into steam and use that steam to turn a turbine, and use that turbine to turn a generator, which contains coils of wires inside a magnetic field. So that's the only way we know how to take fuels and use them to make electricity. All right. So basically, again, so you just have a coil of wires that's spinning inside a magnetic field, and that causes electrons to move in a wire. But in order to get these things spinning, I need to use a turbine. And if I'm using fuels, the way I'm going to use that turbine is I'm going to release energy as heat and then use that heat to make steam. So let's just look at a traditional coal-fired power plant. Okay, so I bring in coal, I burn it, releasing chemical potential energy. That energy comes out as heat. I pump in water. That water flows through the system. As it flows through here, it gets hotter and hotter. It turns into high pressure steam. That steam is then pushed against a turbine, causing it to spin, which then spins the coils of wires inside a magnetic field in the generator, making electricity. But if I'm going to keep the turbine spinning, I've got to turn the water back into liquid using a condenser. More on that later. A nuclear power plant is very, very similar. I'm still going to boil water into high pressure steam and use it to turn a turbine to spin coils of wires inside a magnetic field to make electricity. The only difference is instead of burning coal, I'm going to have fission release the heat release heat from nuclear potential energy in uranium isotopes in the fuel rods. That's really the only difference. Now, I will point out here what happens is I'm going to pump water through the core, carrying the heat out, and it's going to go through these pipes here, so that this water passing through here will pick up some radiation, but that radiation is going to be contained within this. And then I pump other water in here, which then boils into high pressure steam. So this is non-radioactive water. This is interacting with the turbine and the condenser. And I have a third water system that's coming in to cool off the steam and then going into the heating, the cooling towers. So both systems have very, very low efficiency, and like around 30%. And why they have such low efficiency is primarily due, there's heat loss in other places, but mainly it's lost here in the condenser. In order to keep the turbine spinning, I have to have a difference in pressure on either side. High pressure steam comes in here, but if I had high pressure steam here, it wouldn't work. So how do I drop the pressure on this side of the turbine? The way you do that is by using cold water to condense this steam back into liquid water. And that means you have to be near a river. You have to pump in river water, carry this heat out, and then put it in the cooling towers. And you're basically carrying away about 70% of the heat energy that's produced in the system. Now, what happens to that heat energy, right? So 70% of the energy is coming out as heat. I'm putting these cooling towers. If you look, here's a diagram. You can see I basically spray a mist and just give it a chance to try to use evaporative cooling. If you remember from chemistry, heat of vaporization is quite high. I'm trying to use that to carry non-radioactive water vapor away, and that carries the heat, most of the heat away, but doesn't carry all of the heat away. So the heat, a lot of the water that's released from these cool towers is still warmer than the ambient temperature of the river water that came into it, and this leads to a thing called thermal pollution, which has a series of environmental impacts that we'll study later in the year. Now, what comes out of the cooling towers in both cases, it is just steam, it's just water, nothing else. It's not pollutant. So when you look at these things, you think you're seeing pollution coming out of them, but you're not. What you're seeing coming out of them is water vapor. However, I will point out nuclear power, which is over here, you'll see these domes, okay, and over here we have conventional power, coal. You see cooling towers in both cases. The difference is you see smokestacks when you're burning coal or natural gas, and here I'm releasing things in the environment that are quite dangerous, whereas what's coming out of this cooling towers is just water. All right, now let's just compare costs. All right, the reason that people like one reason we don't use nuclear power that much is because people are afraid of it, even though they shouldn't be. The other reason is the upfront costs. So the upfront cost of building a coal-fired power plant is about $2 billion, and that plant will make typically about 600 megawatts of power. whereas a nuclear power plant costs 4 times as much, $8 billion. That's a lot of money there, right? It does make twice as much power output. However, it costs 4 times as much to make. Now, it's worth noting that over the course of the lifespan of these 30-year lifespan of these two different power plants, the overall cost of generating energy or electricity is the same. And the reason is because you have to keep buying so much fuel to run your coal-fired power plant compared to nuclear power. You only have to change these rods like once every 3 years. And so even though it's expensive fuel, you're using a lot less of it. So over the course of, say, a 30-year lifespan, the nuclear power plant, the coal plant, give you the same average cost per kilowatt hour. So there's really no reason not to use nuclear power other than that upfront cost and the fact that people don't understand it and they're more afraid of it. Now, why these nuclear power plants cost so much? They cost so much because of the containment structure. I mean, there's other factors, but that's where most of the money goes into. Because the idea is we have to have this large concrete dome because if there's a meltdown, there will be a breach in this core. High pressurized radioactive water is going to get released. I want to keep it contained. Then I'll have this liquid molten reacting uranium mixed with other things in it mess on the floor, and it will start melting on the floor. So I need a very deep concrete floor so it doesn't get out into the environment. And that containment structure is very expensive. That containment structure is what was missing from Chernobyl, and that's why Chernobyl was so deadly. It's because the Soviets were very irresponsible and chose to cut costs by not using a containment structure, a completely unethical move on their part. Now, it's no secret if you're in my class, you know I'm not a fan of coal. Okay, so look at this. Okay, so coal is really bad. It releases sulfur dioxides and nitrogen oxides, which cause acid rain. It releases carbon dioxide. There's no way to burn coal or natural gas without releasing carbon dioxide, and that's contributing to global warming. You could make the argument that the vast majority of global warming is caused, the greenhouse gases, the most greenhouse gases are produced by the generation of electricity. There's also from coal a lot of PM 2.5, and that kills a lot of people every year, as we're going to see in a future slide here. And they also release a lot of mercury and other heavy metals, which tend to bioaccumulate in organisms in the environment. And interestingly enough, there's a lot more radiation released by burning coal than there is by reacting uranium, because the radiation in a nuclear power plant stays contained in the fuel rods, whereas there is trace amounts of radiation in the coal, but we burn so much coal, we're actually putting quite a bit of radiation into it. So it's ironic. People are afraid of coal, of nuclear power because of the radiation, when in fact it doesn't give off any radiation. They're not afraid of coal, although it kills millions of people and gives off lots of radiation. All right, go figure. All right. Nuclear power plants, what do they give off? Water vapor, period. That's the only thing that comes out of a nuclear power plant. Everything else stays where it is. All right. So they're very clean. Blue skies over Korea forever if we just switch to nuclear power, minus what China says. But if everyone switched to nuclear power, we wouldn't have polluted air. Most air pollution comes from burning coal. Now, by the way, one of the reasons that a lot of places are switching over to using natural gas for electrical production is to reduce the amount of PM 2.5 produced, but it does nothing to reduce the amount of carbon dioxide put in the air that causes global warming. Let's talk deaths. All right. Coal is a killer. So last year alone, well, in 2017, the most recent data I came across, World Health Organization estimated that in 1 year, coal killed 1 million people around the world, primarily through respiratory and cardiac problems caused by PM 2.5 exposure. In the past 50 years, it's probably killed about 8 or 9 million people. Now, notice now we're up to 1 million a year. Why? Because as the world develops, a lot more people are burning coal, and they're often burning cheaper coal, which makes a lot more PM 2.5. So, like India, especially, is where a lot of these deaths are occurring. They have terrible air because they're using cheap coal. Now, how many people died last year from nuclear power? Zero. How many died in the last 50 years? Well, about 4,032. So, but here's the deal, okay? In Fukushima, there was one death. That was a worker who had to go into the reactor core. But no deaths have resulted or will result, World Health Organization suggests from their data, from any radiation that was released by, and there was some radiation released from the Fukushima disaster. The accident really wasn't much of a disaster. 3 Mile Island, zero deaths, zero future deaths. The containment structure did its job. Trace amounts of radiation got out, not a problem. But Chernobyl is what really made people anti-nuclear power, because in Chernobyl there was 31 deaths on the site, mostly people again trying to mitigate the situation itself. But a lot of radiation escaped because there was no containment. About 4,000 people have died or will die, World Health Organization suggests from looking at the data. So So, but look at these numbers. 9 million versus 4,000, and yet what's the world choosing? We're choosing coal. It's not cheaper. It's cheaper to build in the short term, but there's this host of problems. I do not understand why the world is choosing coal over nuclear. Honestly, I don't. All right, nuclear waste is what everybody's going to point to. If you say we should go with nuclear power, they're going to be nuclear waste is radioactive for thousands of years. True, but here's it: it is highly radioactive. Yes, it's going to remain radioactive for thousands of years. Yes, but we put it in these special bins that are inspectable, so we can make sure there's nothing coming out of them. Uh, it is true that there is a potential, maybe somehow somebody could get in here and store. So this is you have to keep them secure. That's true, but it'd be kind of difficult to get. I mean, you get irradiated trying to get the stuff. You would not really be able to make a bomb if you got it. You can make a dirty bomb and irradiate places. So there is some security risk. But it's worth noting that if you took all the radioactive waste from the United States has ever produced, in 50 years of using nuclear power, you could fit it in a football field inside these things. Okay. Now let's talk about coal. Coal waste is an enormous problem. You get this coal ash, and there's just these huge ash ponds behind these coal plants, including here in Korea. And so we're talking that there's mercury, there's lead, there's arsenic, there's radioactive substances just sitting here exposed to the rain. Uh, and the rain falls on the stuff and it leaches these radioactive and heavy metal compounds into the groundwater, into the rivers. Because remember, we always build these things next to a river. It's a huge ecological problem, and we produce a lot of it, over 400 million tons, 140 million tons of it a year. So it's the second largest source of waste on the planet, and it's terrible. It's just left exposed to the environment because we don't know what else to do with it. Now, remember, coal supplies will probably only last at most another 100 years. Uranium supplies, if we do it conventionally, will also only last about that time, maybe even less if we switch entirely over to uranium. However, there are new technologies that allow us to extract uranium from seawater, uranium 235 from seawater, which could extend supplies for maybe 300,000 years, but that technology is still under development. And then thorium breeder reactors, we know they work. We've built them, but we haven't developed an infrastructure for how to reprocess the uranium 233 this process. But if we did that, we could power society for millions and millions of years. Okay. So listen, thanks for watching. That's the difference between them. Hope this one has better audio.